In this transmission model example, the unit commitment and dispatch optimization module is demonstrated. Study case 08 unit commitment should be activated. Unit commitment and dispatch optimization simulation minimizes the operating costs of the system over a defined period of time. It allows market data to be integrated into the network model and used for optimizing the generation dispatch. The calculation combines the optimal power flow calculation algorithm with quasi-dynamic simulation and is accessed via the optimal power flow unit commitment toolbox. The optimization can be based on either an AC or DC load flow, and in this example will be run as an AC-based optimization at hourly steps over a period of 5 days. On this page, the objective function is selected. The default is to minimize total costs, but the user can instead select individual cost components to be minimized. In this project, characteristics are assigned to the active power of loads and generating units, and the generators also have cost data assigned, which is required for the unit commitment calculation. Let's look at the unit commitment data of the generating units. The unit commitment page is the same for synchronous machines and static generators. But if a unit is defined as a variable renewable energy source, or VRE, we can only enter costs for curtailment, as it's assumed that the unit is not normally dispatched. In this example, all static generators are flagged as VREs. Let's look now at a synchronous machine. Here, the active power is selected as a control variable for the unit commitment. We can see the operational limits and have selected them so that they will be observed during the calculation. On the Operating Costs tab, we can specify the operating costs locally or via separately defined cost curves. In this project, generic cost curves for each fuel type have been used. They're stored in the operational library. In the generator cost curve, the resulting costs are calculated based on the individual cost components such as fuel costs and efficiency. The emission costs have an absolute characteristic assigned. On day 127, the fourth day of the simulation period, the value of the emission costs is changed from $15 per tonne to $50 per tonne. This is used to illustrate heavily increased CO2 emission costs that could occur in the future. As the emission intensity is higher for coal than for gas, emission costs are more onerous for coal, and so we expect this to be reflected in the redispatch of the two fuel types. Additional redispatch costs can be defined, as well as startup and shutdown costs. And ramp rates and minimum on and off times may be entered here. Returning to the command dialog, on this page the controls are defined. We'll use active power dispatch as a control, with the active power limits being considered. On this page, the power flow and voltage constraints are selected, together with the generator constraints that are to be observed. Any control or constraint selected in the unit commitment and dispatch optimization command is only considered in the optimization for network elements that also have the relevant parameters selected. In this example, we're considering branch flow constraints, which are set to a loading value of 100% for lines and transformers, and voltage constraints for main bus bars with a range between 0.95 and 1.05 per unit. Also, for the southwestern part of the network, a boundary constraint is defined and observed. The boundary flow constraint limits the active power flow to between plus and minus 400 megawatts. There's an option to consider planned outages on the network. In this case, there are several planned outages during the simulation period, but the one which is relevant here is the outage for 3 hours on the generator transformer of one of the nuclear power plants. This will force the unit commitment to ramp down the generation from this power plant and observe the specified downtime of the generator before it goes back online. On the Results Output page, there are options for the recording of results. And from here, the results files can be accessed. The results are stored in a Before Optimization and an After Optimization result file. The Before Optimization results are essentially the results of a quasi-dynamic simulation which are used to initialize the unit commitment. A summary result file is also written. On the algorithm page, the user can select one of the two inbuilt solvers, but there is also the possibility to make use of an external linear programming solver to make the calculation much faster. However, we will use the default CBC solver. The rolling horizon functionality is enabled. This will split up the minimization problem into several smaller subproblems and will therefore result in a faster and more stable simulation behavior of the solver. We will now start the simulation. For a successful unit commitment and dispatch optimization run, it's necessary for the load flow to converge at every time step in the quasi-dynamic simulation because these results are used for the initialization and linearization of the mixed linear integer problem that is solved in the unit commitment. After execution, there are several ways to view and investigate the results. Statistical results can be viewed in a flexible data page or on a graphic. And result quantities across the time period are also available and can be visualized using plots. These plots show the active power dispatch summed up for the different fuel types. The first plot shows the generation as it would be using a simple quasi-dynamic simulation, and the second plot shows the generation profile after the redispatch by the unit commitment optimization. This redispatch plot shows the changes in output of the different fuel types as a result of the redispatch. We can see the effect of the increased emission cost after day 3. The generation from coal is reduced for day 4 and 5 of the simulation and substituted by an increase of the gas-fired power plants. And the effect of the planned outage of the transformer of the nuclear power plant can be seen. The missing infeed is compensated for by coal power plants. When we look at the outage in detail, we can see that the ramps and minimum downtime are only considered in the unit commitment and dispatch optimization and not in a simple quasi-dynamic simulation. The downtime is extended by 2 hours to meet the required 5-hour downtime for the power plant. This plot shows the interchange of the southwestern part of the network with the rest of the system. We defined a constraint of between minus and plus 400 megawatts for the interchange, and now we can see how this constraint is respected. Inbuilt reports are also available, such as this Optimal Solution report. Here we can see, for example, redispatched energy and costs for generators. We can also use diagram coloring to see immediately whereabouts in the network the redispatch energy or redispatch costs are incurred. Redispatch costs are the costs associated with the generation changes compared with the default quasi-dynamic solution which have been made in order to minimize overall costs. A final feature to look at is the loading of results, accessed via this icon. This allows you to load the time sweep results from a result file to investigate the individual time steps in a single line diagram or a network model manager. Note that the AC load flow result quantities that you're interested in first have to be selected for recording before the calculation is executed. To find out more about applications of the unit commitment and dispatch optimization function, take a look at the video that comes with the Texas grid example.